What's up, my stat stars? Welcome to the Unit 5 summary review video for AP Statistics. This unit is over sampling distributions, and it might be one of the easiest units, but also one of the most important units because basically it connects everything we've learned so far this year to what we're going to learn next, which is inference. And this is the unit that connects it all together, which makes it super important. So before we begin, let me of course remind you of two things. First, this is just a review video. It does not cover every teeny tiny detail that you learned in class. It just covers the real big concepts that you're going to need to know to prepare for your unit test or for the AP Stats exam in May. The second thing you need to do is get out that study guide if you haven't gotten out already. Download it, print it, whatever you do, get ready to fill it in as you watch the video, or feel free to fill it in while you're watching the video or even when you're all done. I don't really care, but that study guide is going to help you tremendously in terms of practicing all the different skills that we talk about in this video. So without further ado, let's get ready to rock and roll with sampling distributions. Now, before we dive too deep into sampling distributions, the very first part of Unit 5 is really a review over the normal distribution. It's actually called the Normal Distribution Revisited, because we want to quickly revisit the normal model and remind you all the key aspects of it. The normal distribution can be used to model continuous random variables that, of course, follow a normal distribution, which many continuous random variables do. But I guess we should probably quickly remind you what a continuous random variable is. A continuous random variable is a variable that can take on any numerical value within a specified domain. And any interval within that specified domain has a probability associated with it. The one thing, unfortunately, you cannot do with a continuous random variable is find the probability of an individual specific numerical outcome. Discrete random variables, yes, you could do that, but not with continuous random variables. All we could do is specify an interval, meaning a lower value to an upper value, and within that interval, we could use, hopefully, the normal distribution if the continuous random variable follows a normal distribution. But if it does, we could use the normal distribution to tell us the probability of a particular value of that continuous random variable falling in that specified interval. So here in this picture, we see a normal distribution, and of course, hopefully remember, a normal distribution is entirely ran by two values, the mean, smack dab in the middle, and the standard deviation. And the normal distribution tells us that we can go up 1, 2, 3 standard deviations, down 1, 2, 3 standard deviations as well. Now, we could go further up and further down. Technically, the normal distribution goes all the way from negative infinity to infinity, but what the normal distribution tells us is that 99.7% of your variable or of your outcomes falls within 3 standard deviations. That's -3 to +3. So in this particular picture, what we're looking at is the area between z-score 1 and z-score 2, and the area in between represents the probability that an outcome of the continuous random variable will fall in that interval. And once again, we could find that probability using a z-table, if you know how to use those. They're kind of ancient, not too many people use them anymore. Or you could also use technology. There's plenty of websites out there, including the TI-84 calculator, which has that normal CDF feature that again can find that probability in between two z-scores. Now, we've already covered a ton of the normal distribution way back in Unit 1. I have tons more videos on my YouTube channel about normal model calculations, but let's actually take a look at an example right now so we can quickly remind ourselves how the normal distribution works. Maxie's been saving money each month for a long time. The amount she contributes to her savings account each month follows a normal distribution with a mean of $55.20 and a standard deviation of $8.15. So here we're working with a continuous random variable, x. How much money does Maxie contribute to her savings account? We know the mean, we know the standard deviation, and we know that it follows a normal distribution, which means that life is going to be really easy for us. Now, the first question here is, what is the probability that next month she contributes more than $60? So the first thing we have to do is figure out, on that standard normal model, where does $60 fall? And that's, of course, by finding the z-score. So we take 60, the value that we're asked about, subtract the mean, divide by the standard deviation, and we get our z-score, in this case 0.589, which I've marked with the red line. Then we want to find the probability that a particular outcome, how much money she contributes, is greater than 60, which is equivalent to a z-score being greater than 0.589, which I have shaded in red. And again, you could use a z-table or you could use your TI-84 calculator to find that probability, and we get 27.8%. So there's a 27.8% probability that in any given month she contributes more than $60. Here's a second example following that same problem. This time we're asked what amount of money would indicate the top 5% and bottom 5% of contributions. So once again, we have that normal distribution set up, and what we have to first do in this case is find the z-scores that represent that bottom 5% and that top 5%. Now once again, how do you find those z-scores? Well, you could use a z-table in backwards, or you could go ahead and use invert norm on your TID4 calculator. And again, we've already learned all that back in Unit 1, but if you know how to do all that, you could quickly get the z-score that represents that top 5% and bottom 5%, which is a z-score of either negative 1.645 or positive 1.645. Then what we could do is take those two z-scores and plug them into our z-score formula, where we already know the mean of $55.20 and the standard deviation of $8.15, and we could back solve for x. Multiply by the standard deviation, add the mean over, and we get our two individual values that represent that bottom and top 5%. So any value above $68.61 would represent the top 5% of contributions, and anything below $41.79 would represent the bottom. Now let's continue here with another example. This time we're going to bring in another person, Cassandra. She contributes on average $62.45, but her standard deviation is $12.66. So a great question we could ask you here is, let's combine them together. What is the probability that the total amount saved in a month for both Maxie and Cassandra is greater than $140? Now, we're not just talking about Cassandra, we're not just talking about Maxie, we're talking about both of them together. So the first we have to do is find the mean and standard deviation for their total contributions. So for the mean, it's really easy. All we got to do is add the $55.20 for Maxie with the $62.45 for Cassandra, and we get $117.65 for the mean of the total. But what about the standard deviation? Well, hopefully you learned a lot in the random variable unit, so we know how to combine, because we are not allowed to combine standard deviations. What we are allowed to combine is the variance. So Maxie's variance is 8.15 squared, that's just standard deviation squared, plus Cassandra's variance is $12.66 squared. Add up all that variance, throw a square root around all of it to get back the standard deviation, and now we have the standard deviation for the total, $15 and about a little bit more than 5 cents, 15.056. I know that really with money you want to keep a third decimal, but I'm going to do it anyway just for accuracy. So now that we know the mean and the standard deviation for the total, we can now answer the question, what is the probability that the total is greater than $140? Of course, the first thing we need is the z-score for $140. So we're going to take 140, subtract the mean, divide by standard deviation that we just found, and we get a z-score of 1.484. So asking about the total being greater than $140 is the same thing as asking about a z-score on a standard normal model being greater than 1.484. And again, we can use our calculator, we can use a program on our computer, we could use an old school z-table to get the probability of 6.89%. So there's a 6.89% probability that Cassandra and Maxie together contribute more than $140. All right, that's a pretty quick review over the normal distribution. I really hope it made a lot of sense and it wasn't overly complicated. But again, if you're like, I don't remember the normal model, go back to Unit 1, review it real quick, or go back to all of the normal calculation videos I have on my YouTube channel to really kind of hone in on those skills. But it all involves using normal CDF and invert norm on your calculator, or really knowing how to use those z-tables, or if you don't like any of that, you can also use programs on the computer. However, your teacher is teaching you how to use normal distributions and make calculations within it. Now let's dive into sampling distributions. But before we dive too far, let's talk about what samples are for. Yes, again, we learned about samples a long time ago, but let me remind you that we take samples and analyze the statistics of those samples in hopes to estimate a population parameter. That's kind of the whole goal, right? Is to take a sample statistic and use it to estimate a population parameter. Now, let's quickly remind you that a sample statistic is any information that, well, summarizes a sample. We got the mean, we got the median, we got the standard deviation, we got the range, we got a proportion from a sample. But anything that we collect from a sample, the whole point of collecting it from that sample is because we want to learn what might be true for the population parameter that it represents. Now, every sample statistic is a point estimator of the corresponding population parameter. Think of it like this. A sample statistic should point us to what the population parameter is going to be. So again, that's why a sample statistic is called a point estimate of the population parameter. Now we can actually look at a couple examples here. So for example, a sample mean, x bar, we would hope points us to what the population mean, mu, is. Or a sample proportion p hat will point us to what a population proportion p is. Or a sample median, which, sorry, we don't have any fancy symbol for, a sample median would point us to what a population median is. And again, when we're working with medians, we just use the word median. We don't have any symbols for them. And then another example would be the sample range. We would really assume that a sample range would point us to the direction of what a population range is. But the one thing we do have to remember is sample statistics are never going to match a population parameter perfectly. We actually have a name for this. It's called sampling variability. The idea that when you take samples, they are going to vary not only amongst themselves, but they're going to vary towards what the population parameter is. They're never going to match it perfectly. Now imagine we start sampling. That is to start taking repeated samples of the same size from the same population. Now, there's a couple rules when we do this that have to be true if everything that I'm going to talk about in this video is going to make sense. First, the samples have to be random to avoid bias. And second, the samples must be independent of each other. Now, the only way we can guarantee independence between our samples is if we sample with replacement, which means once we take out, we put them back. Take out, analyze, put them back. But unfortunately, we don't always do that. So if we are sampling without replacement, then we do have to make sure that our sample size n is under 10% of the population. Now, a lot of kids just remember the under 10% rule, but they don't really understand why. The idea is this. Think about if you have a small bag of M&Ms and you're going to take out a sample of 10. Before you know it, you're not going to have any M&Ms left in the bag to even take out any more at all, and all of a sudden your samples are, well, not independent of each other. Because if you take out 10, what happens next is certainly going to be impacted by what you took out first, because you took out probably 50% of the bag at that point. However, if we go to the M&M's factory where they might have barrels of millions of M&Ms and we take out 10, throw them away, take out 10, throw them away, take out 10, throw them away, well, yes, we technically don't have independence because we are removing M&Ms and not putting them back. But because we're removing such a small amount, under 10% of the population, any differences is considered negligible and it's really just not a big deal. So we're still allowed to assume that we have independence between our samples. That's the general idea of why we need our sample size to be under 10% of the population to assume independence when we are sampling without replacement. So as long as we meet those rules, random samples and sample size that are 10% of the population, then we could start sampling. So now that we've taken a look at sample after sample after sample after sample, and from every one of those samples, we collected a statistic from each of those samples. So essentially, right now we have a bunch of statistics. And with all those statistics, we can create a sampling distribution. A sampling distribution of a statistic is the distribution of values for the statistic for all possible samples of a given size from a given population. Now you might be like, what was that? Let me try to explain. For example, imagine we're analyzing a quantitative variable. So we get a bunch of samples, and from every sample we calculate the sample mean. Okay, now all of these sample means are quantitative variables because each sample mean is a numerical value. So we can create a distribution of all the sample means. So again, picture it. We got a whole bunch of sample means. We're going to collectively look at them all together, and that distribution of all the sample means would be a sampling distribution. We could do the same thing with a categorical variable. Now, if we have a categorical variable, what we could do is we could collect a bunch of samples and we can find the sample proportion from each of those samples. So we'd essentially have a bunch of p hats, p hat after p hat after p hat after p hat. And again, every individual p hat is a quantitative variable itself. And we could take all those p hats and create a distribution of them. And that distribution would be the start of a sampling distribution for a sample proportion. Now, we could do the exact same thing with medians. We could take a median from every single sample we get, and then we can make a picture or a distribution of all of those sample medians. And again, we can do the same thing for ranges. We can take a whole bunch of samples, and from every sample, calculate the range, and then make a distribution of all those ranges. So again, that's what a sampling distribution is. It's a collection of all possible sample statistics for all possible samples of a given sample size from a given population. Now, there are lots of sample statistics out there, but by far the two most popular that we're going to analyze in this unit and in more to come is the mean of a sample mean, x bar, and the sample proportion, p hat. Let's take a look at a couple of specific examples for sample means and sample proportions. Now, let's say in a large city, 65% of all registered voters are going to vote yes on an issue in the next election. Now, we can simulate taking repeated random samples of size 150 from the population of all registered voters. Now, let's make sure that our rules are in play here. First, they have to be random samples. Second, we would have to assume that 150 registered voters is under 10% of all registered voters in the city so that we could assume independence. Now, if we were to take sample after sample after sample, and from every one of those samples, we would collect the sample proportion of people that are going to vote yes. Well, we'd have a bunch of p hats. If we put all those p hats together, we could create a distribution. This distribution is the start of the sampling distribution. Every green dot represents an individual sample proportion. And you'll see that some could be 61%, some could be 62%, some could be 63%. Well, they vary, and that's okay. Actually, that's the one thing samples do very well, is that they vary, and that idea is called sampling variability. Now, when we look at this start of a sampling distribution, we actually notice three things. The first thing I notice is the center. The center is the mean of all p hats. So, okay, let's talk about this. The mean of all the sample proportions. Now, notice it's about 65%, 0.65, right smack dab in the middle. When this occurs, we have what we call sample statistics that are unbiased estimators. If all the samples are pointing us to the truth, they must be unbiased. If the center wasn't 0.65, then the sample estimate would be biased. Now, the next thing we notice is the fact that there is a spread here. They're not all the same. Again, that's why I already mentioned sampling variability. Not all samples are going to match the true population parameter. But as a collective group, the mean of them all will match up with the truth in the center. Now, the third thing I notice is the shape, and the shape is, well, you guessed it, normal. This means we can measure the variation we see in the sampling distribution with some probability. We're going to do some more examples of that later. Now let's do an example with sample means. Let's say that the true mean weight of all cell phones at a large Roosevelt high school, including the case, is 180 grams. Now, we can simulate taking repeated samples of size 45 cell phones from the population of all student cell phones. So again, we're going to take a sample 45, analyze the mean weight of those cell phones, take another sample, another sample, another sample. So we'd have a ton of X bars, and if we take all of those sample means and we create a distribution with them all, we would get the start of a sampling distribution. Now, again, notice three things here. First, the center. The mean of all the sample means. Well, notice it's all piling up around the true mean of 180 grams. That once again means our sample estimates are unbiased. If we were getting all of our sample means to pile up, say around 160, well, that's not the truth. We already said the truth is 180. Well, that would mean that something is biased. Now, the second thing we notice is, once again, not every sample is 180 grams. Some are more, some are less. There's some variability there. Now, we also notice the shape, and that is normal. This is where the central limit theorem, or CLT to abbreviate it, comes into play. The central limit theorem says that when the sample size is sufficiently large, at least 30, a sampling distribution of the mean will be approximately normal. So regardless of what the population of all values look like, the sampling distribution of the mean will be normal if the sample size is 30 or larger. Now, it is important to note that simulating, say, 1,000 sample statistics is still not a true sampling distribution. That is because a sampling distribution needs to have the values for all possible statistics from all possible samples. And if your population is really, really large, like a lot of populations are, that's going to mean a lot, a ton, millions of possible samples, which means millions of possible sample statistics, and we can't possibly simulate them all. But what we can do is create a model for what that sampling distribution could look like and we can really use that model. It's going to be extremely helpful to us. Now, to build a model of a sampling distribution, all we need to know is the population parameters. Now, in this unit, we're going to take a look at 4 specific sampling distributions. Let's start looking at them now. First, let's take a look at a sampling distribution for a sample proportions. First, let's take a look at building a model for a sampling distribution for sample proportions. To create a model of the sampling distribution for sample proportions, we need 2 things: the true population proportion P and the sample size N. Now, when we build this model, it has 3 things: a center, a spread, and a shape. Let's talk about each of those now. So the center of a sampling distribution for sample proportions would be the mean of all possible p hats. Really make sure you understand that notation. It is a mean of all those p hats. And remember, I already said this, the mean of all those p hats should equal the truth, p, as long as we are unbiased. That is why we have a condition attached to this formula for the center, and that is that the samples must be random to avoid bias. Next up, we have the spread or the standard deviation of all those possible sample proportions. Again, remember, we noticed when we took a look at those simulated sampling distributions that every sample is, well, not the same. There is always going to be some spread, which means there's going to be a standard deviation. So the standard deviation of all those p hats can be found by this simple formula. It is the square root of p, that's the true population proportion, times 1 minus p, all divided by the sample size n. Now, in order for the standard deviation formula to work, we once again need those samples to be independent. And again, if we're sampling with replacement, we don't have to worry about that. They will be independent, but most cases we're not. That's why we have to have that condition that I've already mentioned, that samples must be less than 10% of the population to assume independence. Now, lastly, we have the shape, and of course the shape is going to be normal as long as our samples are big enough. Now, how do you know if your sample is big enough? Well, when you're working with proportions, your sample is big enough as long as it has 10 or more successes and 10 or more failures expected in it. Now, when I say success or failure, I simply mean what we're looking for. Like if we're looking for people who are going to vote yes, we need 10 or more of those. And then if we're looking for people that vote yes, the others would be no's. That's what we're calling our failures. So we need 10 or more of those. So the shape of a sampling distribution for sample proportions will be normal as long as the sample is big enough. So you got to make sure you check that you're expected to have 10 or more successes and 10 or more failures. So that's how easy it is to build the sampling distribution for a sample proportion. All you need to know is the center, the spread, and the shape, but don't forget to check those 3 conditions that are attached to each of them. All right, let's take a look at a quick example. Let's say that once again, the true proportion of all registered voters in a large city that are going to vote yes on an issue in the next election is 65%. What would the sampling distribution of all possible sample proportions look like? Well, let's build it. It's this easy. First, we need the center. The mean of all the p hats is going to be the truth. As long as it's unbiased, we should see that center of 65% or 0.65. Now, some samples are going to be higher and some are going to be lower, so of course there is a spread. The standard deviation is going to be the square root of 0.65 times 0.35 divided by the sample size of 150, and we get 0.0389. As long as 150 is assumed under 10% of all registered voters in the city, so we have independence. Now, lastly is the shape, and of course that shape is going to be normal, but we do have to confirm that we have 10 or more successes and failures. So if we take 150 times it by 0.65, we have 97.5 people that are expected to say yes, and 150 times 0.35 is 52.5 people that we expect to say no. So since both of those numbers are 10 or more, we definitely are going to have a normal sampling distribution. Now, I actually built the sampling distribution for you on this page. We see the shape normal, the center 0.65, then I went up 1, 2, 3, down 1, 2, 3 standard deviations of 0.0389, because remember, if you have a normal distribution, you have the mean in the center and you go up 1, 2, 3, you go down 1, 2, 3 standard deviations. So this model allows us to see what all possible p hats are going to look like. Now, as I mentioned earlier, we can also examine the variation within the model using probability. For example, what is the probability that a sample proportion from 150 registered voters is less than 58%? Now, to answer this question, the first thing we need to do is bring in our model. Then we need to identify where is a sample proportion of 58%. We see that it kind of falls on the bottom side. But really, more specifically, we need to find the z-score for 58%. So we're going to simply find the z-score for 58%, and we see that it's negative 1.799. Now we can answer the question, what is the probability that a sample proportion p-hat is less than 58%? That is equivalent to asking the question of what is the probability a z-score is less than negative 1.799, and we could use our z-tables or we could use our calculator to get that probability of 0.0360. Now, another great question we could ask is what sample would mark the top 5% of all sample proportions? Now, to do this, once again, we're going to start with that sampling distribution that we already built, and now we have to figure out where is the top 5%. Well, this is where you could use technology, or you could use your z-tables, or you could use a computer program to find the z-score that represents the top 5%. Now, let me remind you, if you are going to use your 1084 calculator, you want to use invert norm. And when you're using invert norm, you want to put in 0.95 because the top 5% is equivalent to the bottom 95%. If we're looking at the picture here, we see 5% above, 95% below. And when you're using invert norm, you need to put in the percent below or the area below. So that's how we get the z-score of 1.645. That is the z-score that represents where that top 5% begins. Now we just have to use our z-score formula in reverse. We know the z-score, 1.645. We already know the mean, 0.65. We already know the standard deviation, 0.039. What we don't know is the p-hat, the sample proportion that represents that 5%. Then all we got to do is multiply by the standard deviation, add the mean over, and we get a p-hat of 0.714. So if a sample proportion comes back 71.4% or higher, it means it's in that top 5% of all possible sample proportions. Next, we can model the sampling distribution for differences between sample proportions. Here we are looking at possible differences between two sample proportions taken from two different populations, let's say population 1 versus population 2. Now, to build this sampling distribution for the differences in sample proportions, we're going to need three things: the center, the spread, and the shape. Let's start with the center. The center would be the mean of all possible differences between a sample proportion from population 1 and a sample proportion from population 2. And if we think about it, the mean of all possible differences between two samples should be the true difference between the parameter from population 1 and the parameter from population 2. Now, of course, this is only going to be true if both samples are random to avoid bias. Next up is the formula for the spread or the standard deviation. Now, this is the standard deviation of all possible differences between a sample proportion from population 1 and a sample proportion from population 2. A little bit of a tricky formula, but it's given to you on the AP Stats formula sheet, so no need to memorize it. But again, this formula is only going to be usable if we know that these samples are independent of each other. Now again, as long as our sample sizes are less than 10% of the populations that they came from, we can assume independence. But not only do we need to assume independence between the samples in each population, but we also need to make sure that our two samples, the one from population 1 and the one from population 2, are independent of each other. Now, lastly is the shape, and of course it's going to be normal as long as both samples, the one from population 1 and the one from population 2, are big enough, which means we got to check that both samples have 10 or more successes and 10 or more failures so that we're big enough to use a normal distribution. Now let's look at an example that's going to make this whole scenario of looking at the differences of proportions make a whole lot more sense. Let's look at an example that examines two school districts and the proportion of students in each school district that pass a state math test. School District A has 80% pass and School District B has 76% that pass, and we want to model the possible differences between the proportion that pass from a sample of 75 students from District A and 100 students from District B. All right, so the model shows us that the possible differences between two sample proportions could be this. Now we got the center, the spread, and the shape. The center is of course going to be the mean of all possible sample differences. So again, this should be the true difference. The true proportion of those that pass from District A is 80%. The true proportion from District B is 76%. That means the true difference, the difference that we would expect to see from a sample, would be 4% or 0.04. However, again, samples are going to vary, so we have our standard deviation. So here we see that giant square root, and we have 0.8 and 0.2. That is the success rate and the failure rate from District A divided by 75, the sample size taken from District A, plus 0.76 and 0.24, the success and the failure rate for District B, divided by 100, which is the sample size taken from District B. And you can put all the calculator at once, just make sure it's all on the inside of a giant square root, and we get the standard deviation of 0.0629. Finally, we have our shape, of course, normal. As long as we can check, and let's actually check that, you do need to do this on the AP test to prove that we do have those 10 or more successes and failures. So in this sample from District A is 75, 80% should pass, that's 60, more than 10. 20% will not pass, that's 15, more than 10. And the same thing for District B. So since we have enough success and failures, the shape will be normal. So right smack dab in the center, we see the 0.04 that we expect, but we also see that it could be a little bit higher, or could be a little bit lower. Now, a couple common questions here is, what is the probability that a sample of 100 from District B has a higher proportion of passage than a sample of 75 from District A? Now, the model shows us that a sample from A is supposed to have a 4% higher passage rate than the sample from B. But the model also shows us that the differences are going to vary. In fact, a negative difference would indicate that the proportion from B is higher than A, because we built the model based on A minus B. So if B ends up being a bigger value, then the difference would end up being negative. So we can examine the likelihood of a negative difference, which is any difference below 0. So the first thing we have to do is create our model, which we've already done. Then we got to locate 0. 0 difference would be, well, no difference. The sample from A is the same as the sample from B. So if we locate the z-score for 0, which is negative 0.636, anything below 0 would obviously be a negative outcome, and a negative outcome in this situation tells us that the sample proportion from B is bigger than the sample proportion from A. So all we have to do is locate that z-score, which we did, use some type of normal distribution, whether it's normal CDF on your calculator or a normal table, and we got to look below that z-score of negative 0.636 to get 0.262. So there's a 26.2% chance that if you get a sample from each, 75 from District A, 100 from District B, there's a 26% chance that the sample proportion from B will be higher than the sample proportion from A. Now, the opposite of that 26% chance would be the probability that District A is higher, which District A is supposed to be higher, so that's what should be more likely anyway. So answering that question about one sample being more than another is a very common question when you're analyzing the difference between two sample proportions. Next up is a sampling distribution for sample means. If we have a numerical variable and we are examining the mean of the sample, then a sampling distribution could be used to model what all possible sample means will look like. All we need is the population mean mu, the population standard deviation sigma, and of course the sample size n. Now, to build this model, we once again need three things: the center, the spread, and the shape. Let's start off with the center. This would literally be a mean of means. So again, we have a bunch of x bars, a bunch of means, and if we were to take the mean of all those x bars, we should get the true mean smack dab in the center, which would mean that we have an unbiased estimator. Now, of course, we have that condition that the samples must be random to avoid bias. Now, next up we have the spread. Here is the formula for the standard deviation of the sampling distribution. Now, there's two sigmas in this formula, so some kids get it confused. The sigma that doesn't have any subscript, that is the standard deviation of the population. The sigma on the left that has the subscript of x bar, that's the standard deviation of the sampling distribution, which is a standard deviation of a bunch of x bars. That's why the x bar is there. It's emphasizing that this is the standard deviation, not of the population, but the standard deviation of the sampling distribution made up of a bunch of x bars. And to find that standard deviation, we simply have to take sigma, the standard deviation of the population, and divide by the square root of n. But once again, we need our samples to be independent, or at least we have to assume that they're independent, so we need our sample size to be under 10% of our population to assume independence. And lastly, we have the shape of the sampling distribution, which is going to be normal. But this is where we have to be a little bit careful, because there are no such thing as successes and failures when you're working with quantitative data. You have numbers, right? So here's the deal. If we want the shape to be normal, we actually have two different ways this can happen. If the population that the samples came from is already said to be normally distributed, then any sample size is large enough so that our sampling distribution could be normal. Even a sample size of 1 is going to produce a sampling distribution that's normal if the population is already said to be normal. But if the population is unknown or not normally distributed, then we do need the central limit theorem that states that the sampling distribution will still be approximately normal if the sample size is 30 or larger. So let's take a look at a quick example. Let's say that the population of all student cell phones at Roosevelt High School have a mean weight of 180 grams and a standard deviation of 15 grams, and the shape of that population distribution is skewed to the right. Now, what we want to do is analyze what would the sampling distribution look like for samples of size 45 cell phones. All right, we're going to need a center, a spread, and a shape. So let's start off with the center. The mean of all possible sample means would be 180. Duh, we should see the truth smack dab in the middle as long as the samples are random to avoid bias. Now, naturally, some samples are going to be more than 180 on average and some samples are going to be lower. That's where the standard deviation comes into play. So to find the standard deviation of our sampling distribution, we're going to take 15, the standard deviation of the population, divided by the square root of 45 to get 2.236. Now, of course, this is on the assumption that 45 is less than 10% of all cell phones at the high school to assume independence. Lastly, the shape is going to be normal. Now, this is where it's really important. If you heard me right, I said that the population was skewed to the right. So you're like, well, wait a minute. How could the shape of the sampling distribution therefore be normal? Well, that's where the central limit theorem comes in. The central limit theorem tells us that as long as your sample size is 30 or larger, which 45 of course is, then the sampling distribution will be approximately normal, even though the population was not. A really powerful theorem. So once again, in this normal distribution, we have 180 right smack dab in the middle. Then we could go up 1, 2, 3, and down 1, 2, 3 standard deviations. Now, what kind of questions could I ask you based on this model? Well, we could say, what is the probability that a sample of 45 random cell phones has a mean greater than 182.5 grams? So of course, we have to take a look at our model, locate 182.5 grams on our model, but then we have to find the z-score for 182.5 grams. And then once we have that z-score, we could use normal CDF on our calculator. We could use z-tables to find the probability or the proportion above it. So the probability that any sample mean is greater than 182.5 is the same thing as asking about the probability that a z-score is greater than 1.118. And using technology, we get a probability of 0.132. So there's a 13% chance that a sample is going to come back 182.5 grams or higher. Now that's not weird at all. 13.2% probability is not unlikely by any stretch of the imagination. So if I did get a sample mean above 182.5, I'd be like, oh, hey, guess what? Samples vary, no big deal. Now here's another question that we could ask. It's actually pretty popular. Create an interval for the middle 95% of all sample means. So here what we're looking for is what average or what sample mean value to what sample mean value would represent the middle 95% of all possible sample means. So the first thing we have to do is analyze the z-scores for where that middle 95% start and end. Now, if we have 95% in the middle, that means we have 5% left out. That's 2.5 at the bottom and 2.5% at the top. So what we could do is we could use technology, we could use invert normal on our calculator, or we could use some type of website, or we could use our z-tables to determine the z-scores that have 2.5% below it, which is negative 1.96. And then the other z-score technically has 97.5% below it. That would be positive 1.96. But it makes sense that one's positive and one's negative because of symmetry. So once you know that the bottom 2.5% is negative 1.96 z-score, that instantly tells you that the top 2.5% is 1.96, and in between that bottom and top 2.5% would be the 95% in the middle. So now all we got to do is take those z-scores and turn them into sample means by using our z-score formulas. And it's really that simple. Multiply the standard deviations over, add the mean, and we get the beginning and the end of our interval. So any sample mean between 175.62 grams and 184.38 grams would be the middle 95% of all sample means. So of all possible sample means out there for 45 cell phones, or 95% of all those possible sample means are going to be in that interval. The last sampling distribution we analyze in this unit is the sampling distribution for the differences in sample means. Here we're looking at the possible differences between a sample mean taken from population 1 and a sample mean taken from population 2. Now to build this model, you guessed it, we're going to need the center, the spread, and the shape. So let's take a look at them now. The center would be the mean of all possible differences between a sample mean from population 1 and a sample mean from population 2. And the center, or the mean of all of those possible differences, should be the true difference between the population mean from population 1 and the population mean from population 2. Now, of course, the samples have to be random to avoid bias. Now we have the spread, or the standard deviation, because of course the samples are going to vary. So what is the standard deviation for all possible differences between a sample mean from population 1 and a sample mean from population 2? Well, again, it's kind of an ugly formula, but trust me, it's on the AP Stats exam. Formula sheets, you don't have to memorize it, but it's a giant square root, and in that square root, we have the standard deviation from population 1 squared divided by the sample size for population 1 plus the standard deviation of population 2 squared divided by the sample size that we took from population 2. And once again, to do this, to use this formula, we need our samples to be independent of each other, which means we need both sample sizes to be under 10% of the population so that we can assume independence. All right, lastly, of course, the shape is going to be normal, but once again, we have to make sure that we're big enough to be normal. If the populations that the samples were taken from are already normally distributed, then any sample size is big enough, even 3, 4, or 5, but otherwise, we need the central limit theorem. So if our populations are unknown or not normally distributed, then we need the central limit theorem that tells us as long as the samples are 30 or larger, the sampling distribution will still be normal. Let's look at a couple examples that cover looking at the differences of sample means. In this example, we're going to examine the mean weight of 15 male orca whales and the sample mean weight of 10 female orca whales. Now, we start by being told that the mean weight of male orca whales follows a normal distribution with a mean of 12,000 pounds and a standard deviation of 800 pounds, and female orca whales also follow a normal distribution with a mean weight of 10,000 pounds and a standard deviation of 900 pounds. Now, of course, we have to build the sampling distribution by creating the center, spread, and shape. The center is going to be the mean of all possible differences between the mean of a sample of males and a mean of the sample of females. And that is going to be the true difference. 12,000 for the males minus 10,000 for the females is 2,000. So we would expect there to be a difference of 2,000 pounds from a sample of males versus a sample of females. Next up, we have the standard deviation, which is going to be taking the standard deviation for the males, 800 squared divided by the sample size for males, 15, plus the standard deviation for the females, 900 squared divided by the sample size for the females, 10, and put all of that under a giant square root, and we get 351.663 pounds. And of course, the shape is going to be normal as long as the samples are big enough. But wait a minute, our samples are kind of small, 15 and 10. Most kids are going to say, oh, those aren't bigger than 30. But go back. I remember I said that both male weights and female weights of orcas already follow a normal distribution. So sample sizes of 15 and 10, yes, they are under 30, but we don't even need the central limit theorem in this problem because the populations are already normal to begin with. All right, so we have our sampling distribution model centered at 2,000 pounds, but the difference could be a little bit more and the difference could be a little bit less. All right, let's answer a couple questions based on this. What is the probability a sample of 15 male orcas will have a sample mean that is 3,000 pounds or more than the sample mean of 10 female orcas? Okay, so the first thing we have to do is, of course, locate 3,000 pound difference on our sampling distribution. So we see that it's pretty high on the scale there, so we're going to need to identify z-score, which is, of course, 2.844. So now we have to find the probability that the difference between any sample of male orcas, the mean of the sample of male orcas, minus the mean of the sample of female orcas is greater than 3,000 pounds. That's the same thing as find the probability that a z-score is greater than 2.844, and we get a probability of 0.00223, which is pretty unlikely. So it would be weird if we found a sample of males that was 3,000 pounds more than a sample of females. Now, another important thing to start talking about at the end of this unit is what happens when something unlikely actually occurs. So if we look at this problem, we just found out that the probability that a sample of 15 male orcas have a mean weight 3,000 pounds or more than a sample of 10 female orcas is really unlikely, well under 1%. So what if a sample of male orcas really was 3,000 pounds on average more than a sample of female orcas? What would that tell us? Well, here's what you have to understand. In the world of statistics, we do not believe in miracles. So if this very low occurring event actually happened, then that would cause us reason to question. Now, what's the only thing that we could question? Well, that would be the original information gave to us. That would be the average weight of the male orcas and the average weight of the female orcas. So we were originally told 12,000, 10,000, but I would actually say that I don't know if those numbers are right anymore. I would question if those numbers were true in the first place, because we should not see male orcas on average weigh 3,000 pounds more than female orcas, because the probability of that happening is so low. So if it happened, I wouldn't just be like, oh, that's weird, I guess samples vary. No, because the probability of it happening was so unlikely, if it happened, I would start to actually question if the original information given to us was correct or not. Now, the last thing I want to mention in this unit is I want you to notice that in all of the formulas for standard deviation, the sample size n was in the denominator. Now, what that means is that as the sample size gets bigger, our standard deviation gets smaller. That's a really important concept to understand. Bigger samples vary less. Actually, that should make complete sense. Just think about that. If we're trying to use a sample statistic to estimate a population parameter, wouldn't a bigger sample give us a more reliable estimate, an estimate that's closer to what is true? I mean, just think about that. If you're trying to find the average weight of all bullfrogs and you only analyze the mean of 2 bullfrogs, well, it's only 2 bullfrogs. Who knows what you're going to get? You could get something really high, something really low, and all of a sudden you have no idea what's true. But if you were to analyze a sample of 2,000 bullfrogs, well, 2,000 bullfrogs is a lot. Yeah, you might have some big ones and some small ones, but they're going to average each other out because there's 2,000 of them, and you're going to get an overall statistic that's much more reliable and much closer to the true average of all bullfrogs. So again, bigger samples vary less. Always keep that in mind. Now here's an example to actually prove this to you. If we were looking at our cell phone problem, where the standard deviation of all cell phone weights was 15. Now if we have a sample size of 45, we would take that 15 divided by the square root of 45, and we get a standard deviation of 2.236. But if we were to increase our sample size to say 100, we would take that 15 divided by the square root of 100. Now all of a sudden we get a standard deviation of 1.5. Now, again, that's because samples of 100 cell phones are going to be more reliable. They're going to give us values that are closer to the truth. That's why the standard deviation is smaller. So here we see the 2 sampling distributions, the one in blue and the one in red. And we see that the one in blue is more narrow because it has less spread to it, which means it's going to be more accurate. Both of them have the same center of 180 grams because that's what is supposed to be true. No matter the sample size, it doesn't even matter what your sample size is, the truth should be in the center. But we do see that with a larger sample size of 100, we have a more narrow, more reliable, less spread out distribution. All right, that's it for Unit 5. Hopefully it made a lot of sense to you, and hopefully you don't think it's too bad. But keep in mind there are 4 different sampling distributions that we explained to you, and every one of those 4 different sampling distributions has a center, a spread, and a shape. Now, all of those formulas are given to you on the AP Stats formula sheet. It's actually really easy to follow. There's a table for proportions, there's a table for means, and in the proportion table, there's a row for 1 sample, and there's a row for the difference of 2 samples, and same thing with means. So all these formulas are there for you. You don't have to memorize any of them, but you do need to truly understand what a sampling distribution is and how to find the center, the spread, and the shape of a sampling distribution based on the given information to you. So you need those population parameters and you need that sample size, but you also have to make sure that you check all those conditions, because if some of those conditions fail, you might not be normal, you might not be able to use the standard deviation, and you certainly might be biased, which means your center is not going to be where you think it is. So hopefully it all made sense, and how you could actually use those normal distributions to then ask probability questions and answer them is really, really important. All of those types of things are going to be on the AP exam. So hopefully Unit 5 wasn't too bad, but take a look at that study guide and really dive into the different problems I gave to you, how to build the sampling distributions, and how to calculate probabilities with them. All right, see you in the next video. Hopefully you enjoyed it. Talk to you later.